Okay, I forgot it to press that recording button. I've just done it. So I will, in a nutshell, summarize what we did in the past 10 minutes. Today, its attendance is very thin. So what I said is, here is on the screen the general equation that I left you with last time. What were the characteristics of this equation? One, no assumption made regarding particle shape. There is none, right? Nowhere is the spherical, cylindrical, disc, whatever, cube coming in here. No assumption made about the hydrodynamic region, right? Nowhere did we say we restrict this to creeping flow or laminar flow, etc. So in principle, it is valid for the 10 decades of Reynolds number that we had the ambition to do, at least for free settling, right? This is all free settling, right? Single particle settling freely with no interference from other particles. Otherwise, of course, our life becomes much harder. Okay, only then is this, for these assumptions, of course, it's there. That's what we started out with. Then if you were to replace the g by the omega squared r, in other words, you will have a maximal condition velocity of an omega, then within under root twice r into mass into difference in densities between particle and fluid divided through by ap rho p rho into cd, right? Then it was valid also for the centrifugal field. So there was no problem as far as the field was concerned. So then I raised the question, then what is the assumption that we have made? So my answer to that was, well, that you have only, this derivation is only valid for the maximal velocity that arises. And when does that happen? The terminal condition velocity?
In the laminar flow.
No, it will happen whatever the flow field. This is valid. This will happen when the du by
Forces.
dt term, the du by dt acceleration term is neglected in comparison with the other two terms that were there in our general equation of motion, which we derived last time, and I can't keep going back. Okay, so we neglected that term. We said it is small in comparison with the other two buoyancy drag terms, and only then we got this simplification. But we said even that was not required because you could solve the first order ordinary differential equation, all right, also. So in principle, even that is not an issue for us. Okay, but if we took that du by dt term to be small in comparison with the other two terms, we got this general equation, right? So that in principle was the only assumption. So now what is it that I'm asking you to do is take this equation and now derive me a general equation which is valid for a, say, a particular shape, say a sphere, which we know. However, the difference is compared to the first class where we already said RE less than 1, RE less than 1, don't make any such restriction. Let it go from 10 to the power minus 5 to 10 to the power plus 5. In other words, it's valid for any region. So what will those general equations for the terminal condition velocity look like? Whatever be the region of Reynolds number for a sphere, how are you going to derive this? This is the specific question. So can you please do that? And once you have done that, if you can show it to me, then I can go ahead. So essentially, what I'm asking you to do, which you can do for the centrifuge also, is to take the motion of spherical particles and recast the mass of that particle and the projected area. And now put that in the general equation solution that you had and get me the general equation for the spherical particle, whatever be the hydrodynamics. So you are going to take the mass in terms of 1 by 6 pi dp cubed into the particle density and the projected area of the sphere, which is a circle, 1/4 pi dp squared, and you are going to use these expressions in your general UT solution. So what do you get now for the motion of the spherical particle in any flow feed and for any Reynolds number? Okay, you are going to still get a half power dependence for the u subscript t for the velocity. What is the numerical value that is there inside the square root? Can anyone tell me? In other words, if I restrict now the geometry to a sphere and keep all the other generalizations intact, you will of course find a half power dependence for the terminal condition velocity. I just wanted to know what is the numerical value inside the square root, because if you get that right, then I know your derivation is correct.
So it is 4 by 3 dp
Right.
g rho p minus rho l upon rho l into drag coefficient.
Very correct. Very good. Very good. Very nice. So what you had is exactly this expression, right? Please check. Everybody should have this expression. This is a very well-known expression. However, it is a far better expression than the Stokes equation that you started out with. All right. So as you told, the under root 4 by 3 term, difference in the densities times the acceleration due to gravity times dp, the spear's diameter divided by the fluid's density times the drag coefficient. Okay. Now, suppose we were, you see, as I told you earlier, our creeping flow boundary in Reynolds number was 1, right? We said let us assume Stokesian type expression for Reynolds number less than 1. Obviously, if the Reynolds number is even lower, 10 to the power minus 1, 10 to the power minus 2, and so on, dot, 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 whatever Stokes equation that you derived with the maximal velocity scaling a square of the diameter, that will be a closer and closer approximation to the experimental values that we can measure in the wind tunnel or in a settling chamber. But suppose I were to ask you, what sort of maximal error, what is the maximum error that arises from the use of the Stokes' law instead of this general equation for the solid sphere? How will you do that?
So what is the question?
The question is, suppose instead of this general equation, we were to use the specific equation where the left-hand side, in this case the maximal velocity, scales as square of the diameter, which is the equation that you derived in class 1 or 2. If you were to use that instead of this particular equation, what sort of maximum errors are you going to get? Or how will you rather find this? A more interesting question. Obviously, if you have to find this, first you have to determine at what condition will the error between this general expression and the Stokesian expression be the maximum. That's the first thing. Second, you have to know that at that condition, what value of whatever is the unknown, say drag coefficient or so, or velocity, okay, both are related by this equation, would be predicted by the use of the Stokesian equation, which you know the equation. So in other words, if that were the theoretical one and the experimental one is what comes from this particular value, then you can compare the two values and you can tell how much error is derived, obtained for the velocity. So let me give you a hint. Obviously, the Stokesian expression is a very good approximation at 10 to the power minus 5 Reynolds number. A very small value, pure viscous flow. As you gradually start increasing the Reynolds number to 10 to the power minus 4, 10 to the power minus 3, it still works very nicely, the Stokes expression. but it will start deviating gradually from the experimental value or from the general expression that you have here. So, and this deviation will progressively keep on increasing. So obviously the maximum error that you are going to have is at the boundary, and this boundary we have kept as Reynolds number 1. So obviously you should test the Stokesian as well as this general expression at Reynolds number 1. Or if one has the data, one should test the Stokes expression prediction and the experimental value at the boundary between the creeping flow region and the next region, let us call it laminar flow region, at Reynolds number equal to 1, because that is where I expect the maximum error. Now, the question then can be recast as, what did the Stokesian predict at Reynolds number 1? Obviously, it made no specific prediction for terminal condition velocity, because as you know, that depends on acceleration due to gravity, that depends on viscosity, etc. However, if I were to set the particle Reynolds number equal to 1, it did make a prediction as to what the coefficient of drag was if Stokes equations are valid. What is that number? See, the prediction that was made is by the Stokesian was that this drag coefficient varied inversely as the particle Reynolds number. So if it varies as 1 by Re and I put Re equal to 1, then the value of the coefficient of drag that you are going to get will be that constant value that is in the numerator of this expression for the Stokesian region that you get for the drag coefficient as some constant upon Re. So can anyone tell me that constant? Because if we know that value and we take that value at Reynolds number 1 and compare it with the experimental value at Reynolds number 1, then we will be having a nice comparison. And of course, the experimental value at Reynolds number 1 and the general equation for sphere for any Reynolds number that is there on your screen, if you were to restrict it to Reynolds number 1, you will get a value which is almost equal to the experimental value. That is also a very good assumption. That is true actually. So if you compare these two, how much error are you going to get was my question. And say error in the velocity, because you know the equation in general, how velocity varies with g, rho p minus rho, cd, etc., etc. Okay, I'll take a further step. Let us try the next. I haven't yet given the answer, but basically that number that we are looking for from Stokesian is the constant which the inverse variation of CD and Re is related by the constant 24. Okay, so if I impose Reynolds number 1, I'm going to get a drag coefficient of 24. So now, if we use general equation or if we compare it with experiment, we obtain a drag coefficient value of about 26.5. That is what a large number of experiments have shown. Now, comparing these two values and using the variation that of U terminal with all the variables in the system that we have for the general spherical case, how much error is incurred? Maximum. The maximum was at RE1, right? How much percent approximately? Okay, if you don't want to find the error, what I would say is, why don't you derive now the equation for the region RE less than 1? Because I have already told you how the drag coefficient varies inversely and what the with Reynolds number and what the constant is. Now use that information and derive me the terminal condition, which should give you me the Stokesian. So can you at least verify that? In other words, what you should get are these equations. And the last equation on the slide is the equation that we originally had, but only valid for Reynolds number less than 1. Right? So you have to derive me these three equations, and I have put this question. At RE particle at Reynolds number 1, the CD obtained by the general equation, which is what is FO obtained by experiment, measures 26.5 instead of 24. What is the error that is incurred in this approximation of Stokes' law? Of course, if I go beyond RE less than 1, I go to RE greater than 1, it will give me much more errors. But in that range, what is this maximum is what I have asked you to find. So please work these two out. And then let us worry about the range that lies beyond RE greater than 1, which is also of great interest to us. For instance, in Formula 1 type cars, the type of drag that you have is all in the turbulent flow. So RE less than 1 is the crudest type of approximation, right? So, but anyway, please answer these two questions and we can discuss it tomorrow. And then I want to take the case of the laminar flow region, and then I want to take the case of the turbulent flow region, or vice versa, I don't know. And then we will discuss some more interesting facets of the entire region. Okay, so we want to make that progression. First, we are now at RE1. I want you to find the maximum error incurred by the use of the Stokes' law. Of course, before that, I would like you to derive the equations that are there here, which is, I think, quite straightforward for you. And the error, you just have to do a little bit of thinking. And then you have to think what I'm going to do if I were to extend this beyond RE greater than 1, when the Stokes' law itself fails. In that case, I want to discuss tomorrow. A harder case, more interesting as far as I am concerned. Okay, so what is it that we have done? The quorum was not met today, so I have gone back to the general equation that we derived, which was independent of shape. Then you limited that to a general equation for a sphere. And then I asked you some reasonable questions on how you would obtain the Stokesian that you were familiar with from JEE time, and what approximations or what you would make to the flow regime, which was 24 by RE as far as the drag coefficient was concerned. And then I asked you to derive all of this. So it's a better way of doing than assuming the Stokesian a priori, assuming the validity of the Stokes quadratic power to the of the diameter for the terminal condition velocity. Rather, we have a progression where we start from the general equation and then limit it to Reynolds number less than 1. And I asked you how much error is incurred. Maximum. If I were to use, if I would have used the Stokes flow, and I use the general equation that you have. And I gave you the experimental result also, which is the result that you would get from the general equation for the limiting condition of Re equal to 1. And of course, the more interesting thing is what do we do beyond Re greater than 1? Okay, that's what we need to worry about next class. Okay, there are very few people. So anybody, any interaction if you want, any questions, I would be happy to take them.
So the error can be calculated using differential calculus also, right? I mean,
yes, why not? Why not?
I mean the expression, yeah.
Error can be calculated the way you said it, or the way we have been taught in lab reports. You know, I mean, you remember
Exactly.
physics, this error, this plus this plus this. But the error can also be calculated by looking at, for our case, by looking at the general equation for the sphere and seeing what is the functionality with respect to the drag coefficient. And then since we know the experimental value compared to the Stokesian, which is, I told you, the same as the Stokesian versus the exact value obtained by the general equation. And since we know to what power, since we know how the variables scale with respect to the terminal velocity for the general situation, we should be able to get the error. Okay?
Yes.
Very nice. So tell me that, and then we will take the more important. Well, everything is important, but for me, the newer situation beyond the creeping flow region. All right. Okay, but generally, you know, I would like quorum to be there at least 20 odd people. Otherwise, it does. We have to change it and make it in a different way. I don't mind, but because otherwise, you know, one can as well record it and be done with it. You know. Okay, no problem. Either way, I mean, I don't mind if there are fewer people, but then it should be an interaction. No problem. We will finish this, and we'll try to finish next time. And I think we want to do 2 topics before the minor on 15th March, right? So we have enough, just about equal time for both topics. Okay, so we hope to finish this tomorrow or the next, or maybe the next Wednesday, and then start the new topic, which we will finish by March 15th. Okay, all right. Thank you so much.
Thank you, sir.
Thank you.